We're talking Taylor and Maclaurin series today. The goal is to express certain functions as power series. And so what do you need to remember? A power series is a series of the form sum n equals 0 to infinity of some sequence involving n's, right? The formula for the nth term just involves n, it doesn't involve x, times x minus a to the n. This is a power series centered at a. So the big theorem, you guys, is if a function f has a power series centered at a, then, well, we can write that function like this. Now, so this is the power series, right? What I'm about to tell you is what the c sub n equal. Guaranteed, if that power series exists. So f of x would equal the sum from n equals 0 to infinity of the nth derivative evaluated at a divided by n factorial times x minus a to the n power. So this is essentially saying that c sub n is equal to, okay, this notation, this looks like an exponent of n, that means the nth derivative. This is basically saying that c sub n is equal to the nth derivative evaluated at a divided by n factorial if the power series exists. So let's write this out longhand so that you get a feel. It's often going to be convenient to write it out longhand, and you'll get a feel for how easy it is to remember this formula. What we're saying then is that the first term in the power series is just f evaluated at a if we agree that when n equals 0, f with the 0 superscript a is just f of a. So when n equals 0, think about it, you plug in 0 down here, you get 0 factorial, which is 1. And then x minus a to the 0 is 1. So you just get f of a for the first term. And then writing it out longhand, next you plug in n equals 1, which means you're taking the first derivative, we'll call it f prime here, evaluated at a, divided by 1 factorial, that's just 1, times x minus a to the 1 power. That would be the second term. And then plug in n equals 2, you'd get if you plug in 2 up here, that means the second derivative, and I'll stick with the prime notation for now, but I'll change it when it gets to be too many of them. So that means second derivative evaluated at a divided by, okay, n for the third term, since n is starting at 0, n is 2, so that means divided by 2 factorial. It was 1 factorial over here, but I just didn't bother writing that. And of course, 2 factorial is just 2. Times x minus a to the n, which is just 2, so x minus a squared. Now you get a feel for it. What's the third term going to be? Okay, I'll just, you can use 3 primes, but I'll use just the 3. So that means the third derivative of f evaluated at a. 3 factorial, right? Times the quantity x minus a to the third power, and then so on and so forth. This is where we agree that f to the 0th derivative evaluated at a is just f of a. So yeah, and that's a notational item, just like 0 factorial. We agree that that's 1 because it makes our formula work, and same thing here. We agree that f superscript 0 means just the function itself, f. And then it makes the shorthand notation work, otherwise it wouldn't work. Okay, note number 1, the above series is called the Taylor series for f of x centered at a. If a equals 0, the series is called the Maclaurin series for f. And then, very important, the theorem says that c sub n, I mean, if you think about it, the generic power series we developed last time was sum n equals 0 to infinity, c sub n, x minus a to the n, right? This theorem then is saying c sub n is the nth derivative evaluated at a divided by n factorial. Okay, let's prove it. f of x, write it out longhand. What is this formula say f of x is if you write it out longhand? The first term is c sub 0 plus, what's the next term? C sub 1 times x minus a plus c sub 2 times, well, there you go, plus, you could do this the rest of your life. If you ever go to prison, just do this. They'll let you out on an insanity. Okay, c4 x minus a to the 4th power. Let's go to 5, I guess. c5 x minus a to the 5th. Agreed? That's what the power series, the original power definition of power series looks like longhand. Yeah? Let's take derivatives. Oh, fine. Plus dot, dot, dot. Okay. So the first derivative, what would f prime be? What happens to c naught? C sub 0? 0, so you'd get c1, right? For this first guy, you take the derivative of c1 times the quantity x minus a. It's just going to be c1. Because, well, depending on how you look at it, if you wanted to really see it, you could distribute the c1. You take the derivative of c1x, that's c1. Take the derivative of minus c1a, that's 0. But you don't have to do that distribution to see it. OK, what's the next term? Bring down the 2. 2c2 x minus a to the 1 power, right? OK, let's go through this fast. What's the next one? 3c3 x minus a squared, right? Plus 4c4 x minus a cubed. Now, I'm starting to daydream, so if I make a mistake, let me know. X minus a to the 4th. Does that all look right to you? Plus dot, dot, dot. Yeah, this is like watching grass grow. But we got to do it to prove the theorem. OK. Well, the only thing that's really going to be of interest are the first terms. What's going to be left when we take the derivative of the derivative? What's f double prime? Just 2c2. Sounds like do-si-do, right? And then plus what?
6.
Right, but if we want to see a pattern, let's write it as 2 times 3 out in front, or 3 times 2, I guess. c3 x minus a to the 1 power plus what? 4 times 3, c4 x minus a squared plus 5 times 4, c5 x minus a cubed plus dot, dot, dot. I know, very exciting. We'll just do only 3 more. The third derivative, okay, what's the first guy going to be? So this guy goes to 0, right? So just 3 times 2 times c3. We're developing a pattern in case you're wondering. And then take the derivative of this next term. What do you get? 4 times 3 times 2, c4 x minus a. And then take the derivative of this guy. What do you get? 5 times 4 times 3, c5 x minus a squared. We'll just do one more. I'll bet you'll be able to see it after we do one more if you haven't seen it already. Fourth derivative. Fourth derivative, evaluated at x, what do we get? So this guy's gone, right? 3 times 2 times c3 is a constant gone, and we're left with 4 times 3 times 2 times just c4. And then what's left plus 5 times 4 times 3 times 2, c5, x minus a. Did I miss anything? I knew I forgot something. Plus 2, or times 2, I mean. So I didn't bring the 2 down. Let me, although it's not going to affect you seeing the pattern, let me get it right. So times 2 right there. OK. Now, let's examine this last one. evaluated at A. So what would the fourth derivative evaluated at A be? Well, what's going to happen to every term after the first term since you're evaluating at A? Every term after the first term has a factor of x minus a to some power in it, right? So you throw in x equals a, you get a minus a, that gives you a 0 factor, so the whole term zeroes out, which means every term zeroes out after the first one. So you get the fourth derivative evaluated at a is equal to 4 times 3 times 2 times C4, right? So what do you notice about 4 times 3 times 2? How could you write it using a notation we've been using a lot? 4 factorial. So 4 factorial times C4. So the fourth derivative at evaluated at A is 4 factorial times C4, or C4 is the fourth derivative evaluated at A divided by 4 factorial. But this pattern is going to extend to the nth derivative. So the nth derivative evaluated at A is going to be n factorial times Cn, right? And if you don't believe me, just take a few more derivatives. It's great fun. Convince yourself, and then solve for Cn, C sub n, and you get the nth derivative at A evaluated at A divided by n factorial, and that's it, which is what we wanted to prove, which is the result we were looking for. Does that make sense? We're almost to the series Hall of Fame. It's going to be great excitement. But first, before we get to the series Hall of Fame, let's find one of its members in terms of a power series. Find the Maclaurin series for f of x equals cosine of x and determine the interval of convergence. So, all right, what's a Maclaurin series? I haven't written it out. So a generalized power series centered at A would be the sum n equals 0 to infinity, the nth derivative evaluated at A, divided by n factorial, times x minus a to the n. For a Maclaurin series, a equals 0. When you see Maclaurin, that just means a equals 0. So what does the series become? The sum n equals 0 to infinity, the nth derivative evaluated at 0, n factorial times x to the n. A little nicer to look at, right? So that when you write it out longhand, you get, well, what's the first term? Just f of 0, right? Plus, what's the next term? F prime of 0 times x over 1 factorial. Plus, what's the next term? F double prime of 0 x squared over 2 factorial, or 2. Do one more. What's the next one? Triple prime evaluated at 0 over 3 factorial times x cubed, whoops, plus dot, dot, dot. So that's what it looks like when you write it out generically longhand. Would everybody agree with that statement? You okay with that? So that tells us if we want to find a particular Maclaurin series for a particular function, we need to take a bunch of derivatives, don't we, and look for a pattern. So we can hopefully get a formula for the nth derivative. Once we get a formula for the nth derivative, we're in. We've got our power series. So let's say this. Come on. So we look for a formula for the nth derivative evaluated at a. In this case, a is 0. Which means take derivatives. So I'll say that. Which means find several derivatives of f and look for a pattern. Or look for a formula, same thing. So what is f of x? Cosine of x. F prime of x is going to be negative sine x. F double prime? Negative cosine x. F triple prime? Sine x. Okay, I'm tired of using this prime notation, so the fourth derivative, cosine, and then we've brought it around all the way around, haven't we? That might be enough to see a pattern, but just in case, the fifth derivative, negative sine x again, and the sixth derivative, negative cosine x. Okay, I'm tired of this. Now, remember what we have to do. So on this side of my little chart, I've got the nth derivative where n starts at 0, evaluated, or nth derivative of x, right? I haven't evaluated it anywhere yet. But we have to evaluate it at a value of 0, right? A equals 0 in this case. So let's do that on the other side, and it's pretty easy, right? What's the cosine of 0? 1. So over here we have 1. What's the sine of 0? 0, negative 0 is still 0. Negative cosine of 0 would be negative 1. Sine of 0 would be 0. Cosine of 0 would be positive 1. Negative sine of 0 would be negative cosine of 0 would be negative 1. Okay. So every other term is going to be gone, right? Because of the 0 factor. Go back over here. We're filling this in essentially. Or we will be. And you can see every other term is going to be 0 because every other term, once you evaluate it at 0, is 0. So like the f prime of 0, this term is gone. F prime of 0 times x is gone. Right? So let's go ahead and fill it in now. I think we'll see the pattern once we fill it in. So assuming this power series exists, we could say what? If you write it out in longhand, the cosine of x is equal to f of 0, which is, so I'm filling this in, you guys, f of 0, 1, right? F prime of 0 times x, 0. Plus f double prime of 0, first of all, what is that? Negative 1 over 2 times x squared. So how about just minus x squared over 2? Does everybody see that? So that's for this one. You know, in fact, just since it's the first time we've ever done it, let me go ahead and let me put a copy of this formula down here so you guys can really compare it. Whoops, let's try that. Might be faster just to write it again. But I like copying and pasting, damn it. I mean, darn it. Keep it rated G. Okay, erase. Okay. And then just so we can really compare it, this term is the negative x squared over 2 factorial, just 2, right? Then what's this term going to be? 0. And then, okay, well, the next term is going to be what? Positive or negative? We know it's positive 1 times what? So in other words, the next term is going to be the fourth derivative. Evaluated at 0, that's the 1, right? So the 1 goes in, so I didn't write it down, but the next term, if you want to write it down, would be the fourth derivative evaluated at 0 divided by 4 factorial x to the fourth. Right? Plus dot, dot, dot. So what would that be? Plus 1, we already said, times what? So x to the fourth over 4 factorial. I don't think I need the power series anymore. I think I see the pattern. If you didn't, just go out a couple more. What do you think the next one's going to be? 0. But then the next one? Minus. x to the 6th over 4 factorial. 6 factorial, excuse me. 6 factorial is what I meant. Right? And then the next one would be, well, yeah, 0. Who cares about that? Plus or minus? Plus, and then it's going to go x to the 8th over 8 factorial. Okay, now let's get rid of the stupid zeros. Well, they're not stupid. They just don't help. Zeros aren't stupid. That's just not politically correct to say. So 1 minus x squared over 2 plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. I think we got it, right? I think we got the pattern. X to the 8th over 8 factorial. And then I guess the next one would be minus, right? So minus dot, dot, dot. Can we write this in the shorthand notation? So cosine of x is going to be equal to a sum from n equals 0 to infinity. Now, first of all, we know it alternates. So let's get the -1 to the power right. And of course, you have more than one choice. But if we want the first term to be positive, what could we let? Well, if we're starting at 0, though, couldn't we just let it be n? Yeah. OK. And then it's going to be x to a power. Let's start there, and then we'll worry about the denominator, right? OK, what kind of powers do you see? I see even ones. How do you generate even numbers? 2n. And then what are we going to end up dividing by? 2n, the whole thing, in parentheses, factorial. Does that make sense? So this guy, as you might imagine, is in the series Hall of Fame. Now, I'm not going to quite follow my own directions because you've seen so many of these by now. You could use the ratio test to show that this converges for all x. So I'm just going to state that it does, and if you want to prove it, you can. So I, the interval of convergence, is -infinity to infinity, and if you wanted the radius would also be 1/2 infinity, right? No, the radius would be infinity. So that leads us to the Series Hall of Fame. This is one of its members. Well, actually, we have a couple notes first. Note number one is that we have not shown that cosine of x has a power series expansion in the first place. So it's like we're building a house and building the roof first, right? Doesn't always work when you build the roof first, but in this case, it will work. So we have not shown that the cosine of x actually has a power series expansion in the first place. If it does, then the above series is a power series for cosine of x. And let me be a spoiler, it does, and that above series works. Spoiler alert. So number 2, if the above series converges to cosine of x, then we can use partial sums to approximate cosine of x. So the idea is we can use partial sums. We don't have to go all the way to infinity. It might be enough to go to n equals 10 or whatever. To approximate the cosine of x or any convergent Taylor series. In general, we can let, well, remember the SN, S subscript n notation standard for the sum of the first n terms? This is similar to that. We can let T sub n of x represent the nth partial sum of a Taylor series. In other words, that would be the sum from, okay, the role of n switches places when you're using partial sums, remember? So I'll have to use I or k or something like that. I'll use I. So we can use the sum from I equals 0 to n. We're stopping at n. So n is the last thing we plug in. Okay, that's just something you have to get used to. I don't know why it's done that way, but it is. Okay, so what is the Taylor series if you don't let it go to infinity? Well, the formula doesn't change, right? It would be the ith derivative now, evaluated at a, divided by, instead of n factorial, it'd be I factorial times x minus a to the I. And that, I realize that looks strange, but if you think about it and write it out longhand, it's just a polynomial of degree n. So the first term, it would look, if you write it out longhand, it would look just like how we wrote it out longhand earlier, except you would stop it at the nth term. So the first term, think about it, would be just f evaluated at a plus f prime evaluated at a times x minus a plus f double prime evaluated at a x minus a squared divided by 2 factorial plus dot 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 plus the nth derivative evaluated at a over n factorial x minus a to the n. And you stop it there. You stop it there, and you could use perhaps that polynomial to estimate, say, the cosine of x, right? The above partial sum, t sub n is what we call it, is a polynomial of degree n called the nth degree Taylor polynomial of f at a. Let's go ahead and find T6 of x when f of x is equal to cosine of x and a equals 0. And let's use it to estimate the cosine of 0.2. So the way this can get a little confusing if you use the formula directly. So what we're going to do is just write out longhand the sum we developed for the cosine of x and stop when we get to an exponent of 6. Does that make sense? So what we had for that then was, remember it was 1, for cosine it was 1 minus x squared over 2 factorial, which is just 2, plus x to the 4th over 4 factorial, minus, what's the next one? X to the 6 over 6 factorial. Remember that cosine's an even function? That can help you remember this formula, can't it? It means the exponents better be even. And then we would stop there. There's your 6th degree Taylor polynomial for cosine. So then what could we do? Just plug in 0.2, and we'd have 1 minus 0.2 squared over 2 plus 0.2 to the 4th power over 4 factorial minus 0.2 to the 6th power over 6 factorial. Anybody have a calculator handy? Okay, 1 minus 0.2 squared divided by 2 plus 0.2 to the 4th divided by 24 is 4 factorial, right? Yeah. And then minus 0.2 to the 6th divided by, what is 720? Yeah, so I heard you say 1, 1 after the 9, 8. And I was expecting this value. So yeah, just make sure you punch in your calculator. It probably just missed something, missed a button on your calculator. Anyway, I'm getting this value on my calculator for the approximation. So I get that this is 0.9800665778. That's what the calculator spit out. Now, it would be interesting, though, to go ahead and put in 0.2 on the calculator. Let me make sure I'm in the right mode, radian mode. And let's go cosine 0.2. Oh, wow. That's pretty good. So have you ever wondered how your calculator works? I'm not here to make the claim that your calculator uses this approximation to get values of cosine, but it uses mathematics. It doesn't, have them in memory. It can use this sort of polynomial or maybe a different sort of method, we actually don't know because TI won't tell us. Their algorithm for getting it is, well, it's proprietary, right? But it gives you an idea mathematically of how it's done, of how you can get a value for a transcendental function like any of the trig functions evaluated at a point, e to the 5, right? How do you get that? Well, you use a power series or some other way, some other polynomial or some other way to get it. So at least gives you an idea of where some of this stuff comes from. Okay, so finally, we're at the point where we can talk about what you've all been waiting for, the Series Hall of Fame. It's in your book. I believe the page number's right. You can check me on that. So the Series Hall of Fame, some of them you already know about. 1 over 1 minus x is the sum from n equals 0 to infinity of x to the n. And of course, r, the radius of convergence, is 1. And the interval of convergence is just from -1 to 1, right? So that's what you already know about geometric series. Of course, that should be in the Hall of Fame, right? But then sine of x turns out to be this guy. Notice the exponents are odd, and the sine of x is an odd function. It's very important you can write these out longhand. Okay? Yeah?
Can you make it a little bit bigger?
Yeah, sorry. Let me make it a little bit bigger. Let's go. We can't do it. 150. We can do it. Okay. It's very important you can write these out longhand. It will be very helpful to do that. So let's write a couple of these out longhand. Make sure you know how to do it. So what would this guy look like if you write it out longhand? So what would so it's the sum n equals 0 to infinity, -1 to the n, x to the 2n plus 1, divided by 2n plus 1 factorial. So you would derive this the same way we did for cosine of x. Start taking derivatives, look for the pattern. What would you get? What would the first term be if you plugged in n equals 0? So if you plug in n equals 0, what do you get? X. And then it's going to alternate from there, right? Minus, what's the next one? If you plug in x, n equals 1, you get x to the, so you plug in 1 there, 2 times 1 plus 1, x cubed over 3 factorial plus, you plug in 2, you get 2 times n is 2 plus 1 is 5. X to the 5 over same thing factorial. Now you got the pattern. What's the next one going to be? Plus dot, dot, dot. Now, your teacher in trig told you that the sine is an odd function. Here's proof, right? What's an odd function? You take sine of negative x, you can pull the negative out front, right? Why can you do that? Because when you write it as an infinite polynomial, a polynomial of infinite degree, it's not really how we say it in most books, but we kind of think of it that way secretly. You plug in x for negative x, you can factor that negative out and get the same formula you started with, right? So sine of negative x is the opposite of the sine of x. That's why it's an odd function. And so compare that with what we got for the cosine of x earlier. Remember that was 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Cosine's an even function, which again, your teacher in trig or pre-calc told you that as well. Okay? So this, whether or not you want to admit it, this is beautiful. We've turned these complicated transcendental functions, they're called, trig functions are called transcendental functions. We turned them into polynomials in a very real way. Not the kind of polynomials you messed with in pre-calculus, but really they act like polynomials. So what's another cool one? Look how, okay, when I say cool, I mean mathy cool, not real life cool. Look how easy e to the x is to remember when you write it out longhand. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, so on. And then you should be able to write it. It actually looks better in the summation notation. Oh yeah, the sum x to the n over n factorial. It couldn't get any easier to remember than that, right? There's a tangent inverse one that you could derive using the techniques I've shown you. And there's a natural log of 1 plus x one you could derive using the technique from the other day or using power series. That's it. I'll see you next time.